They are all what they grouped into what they call silicon realization. But the new concept they came up with is what they call SoC realization. And this is in, you can think of it as kind of a new domain and a new opportunity, because this is what tries to solve a lot of the problems that have been introduced by all these SoC challenges that I talked about. You know, how do you put blocks together efficiently? How do you create a design where teams are spread out all over the pieces and somebody puts it together? You know, how do you meet your power budget? How do you design with enough visibility early on so you make sure that that chip, when it comes out, is going to meet your product requirements? So this was a very neat way of at least conceptualizing the problem and conceptualizing the different domains of how to solve the problem. So you can think of SoC realization as kind of a catalyst for SoC productivity. It's the things that help you beyond traditional chip design to help you to deal with the unique problems or the special problems that are introduced for SoCs. So things like, you know, defining the architecture, deciding on the hardware software issues. These days, you know, with a lot of software on the chip, you can decide to do pretty much anything in hardware or in software. So making those kind of trade-offs, choosing the correct blocks, they meet your quality and cost requirements, assembling the chips, because now you're playing this Lego game, right? You've got these little blocks, and you're not creating a design flat, you're stitching them together. Doing this early analysis, having visibility into the design characteristics, and making sure you can verify and optimize and do all of that early. So these are all kind of what we consider to be a part of SoC realization, because these are important functions to create an SoC. And we think of it as a bridge. You have these, you have the world of system realization, which is where all the software is being developed, and you have the engine that can make a chip, and you connect the two using the functions provided by SoC realization. So I'm going to show you another way of looking at it. So if you think about it, these are the three levels. This is system realization, SoC realization, and silicon realization. And even within these blocks, there are subcategories, you know, like system realization has, within software development, there is a range of software abstraction. You can have, you know, software which is very close to the hardware, like drivers and stuff. And then you have application software that is far removed from the hardware. So there are different levels of abstraction that you need to worry about. So, and then you have, in addition to, you know, to the three classical, the three functions that come out of the EDA 360 concept, you have verification that spans all the levels, and you have to support this whole business of you know, blocks of IPs, IP quality, IP handoff, and stuff like that. Now, if you think about it, you know, the power of SoC realization becomes obvious when you start looking at the internals of these blocks. So system design, to be able to develop software, I need to have very, very abstract view of the design. I have to have models of the design so that my software developers can write software. But these are very abstract models, and I've got to such an abstract level that it has hardly any resemblance or any connection to the actual underlying physics or the underlying hardware. So it's not a level at which you can explore a lot of things. You can use it to write software, but you can't use it to explore, you know, power, speed, and things like that. And at the level of silicon implementation, you know, you've got so much details. You've got these billion transistors that you can't really do any creative, you know, analysis and exploration. Right? All that you can hope to do is most efficiently implement that thing, but you can't explore these different options and stuff. So the power of SoC realization is that it has just the right level of abstraction. So it has just the right level of information. And it is, you know, at a point where you can explore different things. So it's the right trade-off between abstraction and accuracy. It has enough information. You can start to analyze like power and speed and things like that, an area at that level. So it's a very interesting level to both provide the bridge and provide you with the exploration functions that you need to get an efficient SoC. There are various different businesses and tools that are coming out to support this. You can have a whole ecosystem around blocks and IPs. There are many people that are creating them, as I mentioned, from large companies to mom and pop shops. And there needs to be some level of checking quality, doing handoffs, and then people create a central repository where you make these things available to your designers to use them. But then as they pick it off the central repository and start using them, there is also now there's a need to have further acceptance type of checks. So this is kind of a new emerging business that has popped up in the last couple of years and is getting a lot of traction, mainly because of the prominence of IPs. So what does all this mean for EDA? I'm particularly interested in EDA because that's what I do. That's what I've done all my life. So I see this as representing a game-changing opportunity for EDA. It's defined a new domain which lets you break out from the classical world of EDA and do something new, do something innovative, do something cool, do something that you can build a business on. And the opportunities are, I just expand on a few things, from supporting the IP supply chain to supporting hardware, software trade-offs and co-design and things like that, are all kind of very exciting new opportunities that you can explore. So what is the net result of all this? The net result of all this is to reduce risk and reduce cost of designing an SoC. And the best way to see the impact of that is if you look at the point that I made earlier, that based on the cost of what it takes to design an SoC, you have a limited market that you can target a product. Because the market has to be significantly higher than what it costs you to design the product. But if you can creatively reduce the cost of designing a chip, you can now target a range of new markets. And that is what a lot of companies are doing these days. They're trying to figure out, how can I be very clever so I can design 1,000 SoCs and cater to the China market with their growing demand of consumer products and smart applications. The other thing that I wanted to leave you with, something to think about, is that EDA is a relatively small industry. It's a $4-5 billion industry, and it has, I would say honestly, limited clout in the ecosystem of the whole electronic supply chain. It's a $1 trillion industry, and EDA is a few $1 billion. But this trend is very interesting in that it provides us with some very powerful friends. And what I show here is the market cap of Apple versus ExxonMobil. And as you probably all know, that Apple stock's going through the roof. And Apple market cap today is it's the largest in the world. So in some ways, the point I want to make is that we have some very influential friends. We have some very influential drivers. If you have a wagon, who do you want to hitch your wagon to? To a very powerful engine. And this whole business of SoCs and SoC realization has the support and the interest of some very, very influential and large companies. And that's something we can tap into. We can provide them with unique advantages. We can help solve their problems. So in some ways, we become larger than life by having these very powerful friends. So let me conclude by saying that the industry is certainly very cognizant now of the power of the SoC. People recognize the power of the SoC and its ability to help you create killer apps. The trend has started. You can see large companies making their moves. Intel has a processor called Atom, which is targeted to go into this SoC low power space. Microsoft is porting Windows to ARM. So there are many of these trends that are all indications that these giants like the Intels and the Microsoft are in alignment with what I'm talking about. It does represent a discontinuity for semiconductors and EDA, so it creates opportunities for people to take advantage of. I think SoC Realization is providing a major, is a major component or major enabler of this trend. So people that work in this space or do something with it have an opportunity. And it also creates kind of its own ecosystem. It requires collaboration between different companies. If you think about it, there are people doing block designs, there are people buying and assembling those blocks, people that are making those chips. There are, there's just a whole collaborative, it's like a half a dozen or 8 companies, types of companies that need to kind of work together to bring about an SoC, and that creates new demands for new standards, and also in many ways, new opportunities. All right, that's all I have to say. Thank you all very much.
Now the floor is open for question and answer. If you want to ask anything to Ajoy, we can entertain your questions.
Yes.
You gave us a figure, $100 million for the latest SoC at 28 nanometers. Would you like to, break it down a little, like where does this money go?
Yeah, sure. I mean, there are actually slides, which unfortunately I'm not showing here, but I'll be happy to share more data with you. But I'll tell you what I can think of,
Sure.
off the top of my head. So software represents a good chunk of it. About half of it is software, or maybe even a little more than half. And then you get into the hardware as part of it. Verification tends to be a dominant part of the hardware design. So probably, $30 million or so in verification. Probably 15% or 15 million or so is in the physical design and implementation. So these are the large components, but there is fairly detailed information available on maybe 8 or 10 components that make up the 100 million. And by the way, the 100 million is a very round number. I think the 100 million number has been crossed, and we are probably quite a bit north of 100 million at 28 nanometers. There's another interesting trend that is going on. As you go from node to node, the growth is kind of non-linear. So from going from 65 to 45 nanometers, the things kind of doubled, if you will. The amount of time it takes to do the physical design went up from a few thousand man hours to 2,000 to 4,000. Then when you went from 45 to 28, it went from 4,000 to 15,000. And then going into 22, the projection is it's going to be like 50 or 60,000 man hours. So you can see that the curve is clearly very nonlinear. And that's where, again, a lot of the opportunity comes, a lot of the pain of the cost comes, the pain of iteration and mistakes. So the stakes are getting higher and higher at each technology node, and there are fewer and fewer people that can make them because the cost of developing the process is huge. And there are still a lot of unsolved problems as to how are you going to reduce power and make these things. And the other thing that is very interesting also is that while these designs are becoming more complex and more power hungry, what the industry needs is kind of keeping a flat level of cost. You can't afford to double and quadruple and 8 times from a cost point of view or from a power point of view. So if you look at what the market wants, it essentially kind of wants flat. I want to spend the same amount of money to design a 28 nanometer chip that I used to design a 65 nanometer chip. So very interesting dynamics that are driving the industry. Yes?
So, I had a question about open source.
Yeah?
So, obviously you talked about SoC realization, which certainly means a lot of abstraction of the subjects and the IPs that are out there. And if you look at the software industry, which is the Oracles and the Googles of the world, obviously and Salesforces of the world, they obviously have leveraged the open source concept quite a bit to increase productivity and reduce cost. EDA and semiconductor industry in general, why hasn't it adopted open source?
Well, I can give you a couple of reasons. First of all, the number of people that play with software and the level of software activity in academia is much, much larger than there is for EDA. You have smart kids in universities doing masters and PhDs and developing cool pieces of software. that is a natural way of populating the open source. Secondly, I would say that there are some limited amount of open source type stuff available. There are like what are called open cores, which are IPs that are in the public domain. Now you wouldn't bet your $100 million design on one of these open cores, but they are there. It's very small and somewhat limited. And thirdly, I think and this is probably the most significant point, is that hardware is a lot more unforgiving and intolerant of errors. Mistakes will kill you. Whereas, if you have a software bug, you fix the bug and you recompile and relink and you're off and running. So fixing quality issues or tolerating, somewhat weak quality is much easier to do in software than it is to hardware. So realistically, the hardware is so demanding in terms of quality and so expensive and unforgiving in terms of errors. I think that discourages, the open source kind of trend. But maybe it'll happen, some years in the future. So you can certainly play with open cores. Yes?
Following the first question, when you said the 50 million, half of the cost is software, did you mean the support software that needs to go with the chip, like drivers and other things?
Yes, it's the development cost of the software that will run on the chip. So it will be the drivers and the application software. That if you remember that one slide I showed, there are several levels of software. And that's becoming a growing part because people are using it as a differentiator. So you can get an edge over your competition by providing more software support.
So is that number also true for a chip provider versus a OEM or a system provider? Like a Broadcom or a Qualcomm or a TI?
Yeah. The data that I'm quoting are from companies like that. It is companies that are creating SoCs that provide the software with it before they ship it to, say, the cell phone company or something. And those are exactly the kind of companies that this data comes from. Yes, please.
So what do you see would be the trend of homegrown solutions by companies like Intel or Texas Instruments as the technology nodes shrink from 28 nanometers or lower? Because you said the EDA industry is $5 billion, but looking at powerful friends and influencers, it looks to be a very big industry.
So you're asking about what is homegrown solutions?
Yes. Custom solutions.
Custom solutions. That trend used to be the way things were done. In fact, I kind of grew up in that environment at Bell Labs when there were like half a dozen companies that developed all the EDA in the world, and there was no Cadence or no Mentor or no Synopsys. It has become now pretty much accepted that for any individual company to develop the solutions they need is prohibited. That you need to have some level of the commercial markets, the power of the commercial market to justify or to help justify the cost of developing the solutions. Now, at the same time, I would say that there are some large companies that still maintain pockets of EDA development. It doesn't make sense to develop the commodity type of tools. But if you really believe that you are the first player to get into 22 nanometers, that you'll have some problems to solve before the Cadence and Synopsys and the others will provide you with the solutions, and you will have a small team. But you have to be very selective because the business is very competitive. You cannot afford to spend, and the cost of developing EDA tools is very expensive. I used to work in this environment at Bell Labs where the cost of developing EDA was a couple of $100 million, and the semiconductor size was a few $100 million more. So it was almost like you spent $1 on EDA for every dollar of semiconductors you make, which the economics doesn't work. Yes?
So you keep mentioning that the number of companies that can design these chips are using it. And
the number of companies that can afford, the number of applications that can afford $100 million chips. It's not a shortage of expertise to design. It's the economic justification, which is the bigger barrier.
So what happens to the applications which are less than that number? Who solves it? Do you go old nodes?
You cannot afford to go to the smaller technology nodes very rapidly. You stay at the older nodes, which are cheaper. you look at other lower cost, there are things called FPGAs, as you may know, which are, more off-the-shelf standard products, and they're being very creative. They are trying to provide flexibility so you can do some customization and things like that on an FPGA. So that's, and there is always, standard processors on which you write software. So they have to improvise, in some other ways. You cannot, there's just no way for most people to afford these $100 million chips.
So in this kind of market, how do the EDA companies like yours, how is it like for the customer base kind of reducing?
Well, the interesting thing is that the customer base is not reducing, because what is happening, at least so far, because of the increased complexity, the amount of money that people are spending is it's not growing much. It's going from, 4 billion to, 5-10% a year. And that's, you have to operate within that kind of a growth. It's not a market that is doubling every year. Even though if you look at all the activity and the complexity, you would think, hey, this business should grow much faster, but it is not. So EDA companies, struggle to operate within those boundaries. I think I should wrap up.
Thank you very much, Ajoy, on behalf of NIT. I really appreciate